Okay, good morning, everyone. So let's start our class for today. There is a second class for the defined sensors, what generally used for industrial automation and 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 process control. So apart from the sensors, the basic sensors what we have learned in last classes, like flow sensors, level sensors, pressure sensors, and many more. So there are several sensors are there. I mean, numerous numbers of sensors are there in industry. They are mostly used. They are generally used in industrial automation or safety purpose. And among them, I would actually now there is the time is a limit, so therefore I can't explain all these sensor, but I can give you the mostly used sensor, the name and the working principle of the mostly used industrial sensor. So the first that will be the photoelectric sensor. Now here I will give you some glimpse of how the photoelectric sensor works and what is the working principle of it. So how the photoelectric sensor works? So here in this photo, so this is a typical photoelectric sensor you may have seen in the industry. That is, this is the kind of sensor where you will see some. So this is a sensor. Here there is a transmitter and so okay, this is transmitter and this is the receiver. So if we go for the I mean schematic diagram of this kind of photoelectric sensor, it will be looks like this. So here you have a transmitter and you have a receiver. So transmitter means any kind of electric light source, that may be LED, that may be laser. So by using this transmitter, you are transmitting some lights, and after reflecting from this particular target, if there is any target, so that reflected light will be sensed by a receiver. That receiver is generally is kind of photodiode, which photodiode, if the light is incident on a photo, the current will be generated. So by measuring that current, you can measure the intensity of the incident light. Okay, so that is the basic principle of a photodiode. So if there is a target, so that will be from the light will be reflected. What is the light is transmitted from the LED or the laser, there is a light source that will be reflected from a target, and that will be received, or that will be incident on the photodiode, and that photodiode will generate a current, and by measuring that current you can actually understand or realize that is okay, there is a target. If there is no such target is there, so what happened? So you will not get any reflected light, so your output of the receiver will be zero. That means there is no target. Now here is some important thing is there, that is the range, the scan zone. So there is a, in this kind of photoelectric sensor there is a range. So for example, if this is a scan zone of a photoelectric sensor, and so you can't if there is an object over here, you can't sense that target. Okay, so now coming to the different specification of the photoelectric sensor. So photoelectric sensor generally works with a supply voltage of 10 to 30 volt of DC. You can see in over here also, you can see, can you see this? So if I zoom it out, you can see, so this is the, here it is, you can see DC 10 to 30 volt. So our photoelectric sensor generally works in the range of 10 to 30 volt DC. Not only this, if I come to the output terminal, So output terminal of the photoelectric sensor are of three types: 3-wire, 4-wire and 5-wire. In case of 3-wire sensor, here you will find there are two different types of connections are there: NPN and PNP. What do you mean by NPN or PNP? NPN means from the output, this kind for NPN sensor, the output is generally, I mean, is obvious, it should be the negative supply, negative type, and for the PNP the output is positive type. Whatever the output you are getting from this sensor, that will be positive type. So 3-wire type sensor is either NPN or PNP. In case of 4-wire, 4-wire is a universal kind of sensor. That means in 4-wire photoelectric sensor you will find, you will get both NPN and PNP connection. Okay. Now coming to the 5-wire type, in 5-wire type there is a built-in relay, and that built-in relay, so in this 3 and 4-wire connection there are no built-in delay, but in 5-wire connection you will get a built-in delay. Okay. Now, this is a very basic principle of the gain and sensitivity of this particular photoelectric sensor. If the gain is less than 1, that means the gain means received by necessary. Okay, so there is a calibration over there in this kind of photoelectric sensor for a transparent object, and for a non-transparent object, and for a semi-transparent object. Okay, you may have, you may, if you are, if you have seen the bottle filling industry in any kind of if I tell you that any just I mean water bottle filling industry, in that kind of, they are using the uh, transparent kind of they are using transparent kind of object. So this is the object, so that means they are calibrating their sensor in that way. For example, if you are, if you are working in inventory management, so the inventory is generally of non-transparent object, so objective not transparent, so therefore your photoelectric sensor should be calibrated in that way. Fine. Now coming to the disturbing factors of the photoelectric sensor. So this is a conveyor belt you may have seen in the industry very often. So there is a objectives coming, and this object, the type of the object is mainly the disturbing element. That means if you are calibrated in terms of uh, non-transparent object, if a transparent object come, there may be a problem. So you have to classify these things, or you have to, for if you have a supply line, so this is a supply line, if in this supply line you have both kind of object, so you have to use two or I mean more than one photoelectric sensor. Okay. And the distance means, as I told you, there is a always scan zone for a photoelectric sensor. So the you have to install your photoelectric sensor such a way that the object you want to detect, that should be within the scan zone of the photoelectric sensor. Fine. Now coming to the types of the photoelectric sensors, there are three types. Generally, three different types of sensor are there. So these three types are as follows. The number one, the diffuse reflective sensor. So in this kind of diffuse reflective sensor, the distance is up to 1 meter. This is the shortest range among the all photoelectric sensor. Here the principle of the sensing is as follows. You have a sensor that has a receiver and the emitter. So emitter will reflect the light, that will be if there is a object, the some light will be transmitted through this object, or some light will be reflected back to the receiver. So this is generally used for the transparent or semi-transparent sensing object. So this kind of diffuse reflective sensors are the shortest distance reflective sensor that can be measured the object which is within the 1 meter. And just I forgot to tell you that this is the photoelectric sensors are generally used to detect the proximity of the object or the number of the object, and is what kind of object it is, like transparent or semi-transparent or non-transparent. Okay. Now coming to the second type of photoelectric sensor, that is the retroreflective photoelectric sensor. Here you will see there is a retro reflector over there. So this retroreflector, what it does is it will so you have a emitter once again and you have a receiver. So the reflected light that will be reflected by the sensing object, as well as that will be transmitted. I mean, there will be retroreflector that will also reflect some light. For example, let's start with begin. So when you don't have any object, so what happened, the light will come over here, yeah, and that at the retro reflector, and that will reflect your light, and the reflected light will be received, I mean reflected will be received by the receiver, and by so in that case you can calibrate it that there is no such sensing, there is no such object. Now if there is a object, so that means there is the light which is coming from the retroreflector is very low, I mean lesser than when there is no such object. So by calibrating these things you can measure or you can detect there is a object in this line. So that is this kind of principle, this kind of retroreflective based sensor can measure can be used for distance up to 6 meter. Now the last one, the third one, is the through beam sensor. So it is generally used for long distance range up to 12 meter. So here the emitter and the receiver are two different type, two different identity. That means there is in last two cases you have seen that the emitter and receiver both in this sensor, but here you can see there is one emitter and there is another receiver. So this is very simple. So that's why, and the I mean the receiver, as the receiver and the emitter are two distinct object, two distinct things. So therefore you can measure the long distance up to 12 meter. So very simple. If there is a object, so sensing principle is very simple. Like if there is no such object, so if whatever the light is emitting, that will be received at the receiver. But if there is a sensing object, the transparent is non-transparent, so you will not receive any light in this receiver. But that is a transparent, so that means the lesser amount of light you will receive at the receiver. Fine, right? So that is this is the longest type of, I mean this is the longest type of photoelectric sensor that can be measure the object which is within the 12 meter. Okay. Now coming to the wiring of the photoelectric sensor. So in the wiring of the photoelectric sensor, as I told you, there are three types of photoelectric sensors are there: 3-wire, 4-wire, and 5-wire. In 3-wire sensor, so if this is PNP wiring, so here this is the relay. So this is our photoelectric sensor. So the positive supply is with PNP. So positive supply is connected to the 3-wire. I mean there is a supply which is connected to the photoelectric sensor, and the output of the photoelectric sensor is the positive in type. As I told you that for the PNP wiring, the output what is coming, the command which is coming from the photoelectric sensor, that will be positive in type, positive type plus VDC, so positive voltage. And there is another wire that is the negative. On the other hand, in case of NPN wiring, you will find the command which is coming from the photoelectric sensor, that is in negative in type. See the negative voltage. So the relay you have connected, so the negative terminal of the relay is connected to the photoelectric sensor because it is a NPN wiring. Fine. Now this is a four-wire photoelectric sensor. Here, as I told you, you can get both NPN and PNP connection. So here you can see that is the brown wire is for the positive supply, the PNP, and the blue wire for the negative, that is NPN supply. And there is another two output are there, that is the it is gone wrong. So negative and positive, these are for the supply voltage plus 24 or whatever the supply voltage you are giving, and these two outputs are for the negative. This black is for the negative and the pink is for the positive supply, positive command, sorry, these are for the supply and these two are for the NPN and PN. Now coming to the 4-wire type, as I told you, in 4-wire type there is a relay. So here once again you have brown and blue, that is the supply, positive supply, and the negative or the common supply, and you have the NO and NC. So these are for the what? These are for the relay connection. So these are the, if you connect normally open and normally closed. So in 4-wire type of photoelectric sensor, there is inbuilt relay, and you can directly connect this NO and NC connection or this wire to any external thing to control that switch. Okay. So and there is also another port, that is the common terminal is there, or you can also use in any other purpose like commanding or sourcing this photoelectric sensor to other circuits. Now coming to the torque sensor. So torque is, the torque is generally measured if you apply a force on something. So the rotational thing, what is the rotation of this particular object is the torque. So that means if you apply a force, so after applying a force, so what is torque? Torque is measured of a force that can cause an object to rotate about an axis. For example, you have any fan. If the fan is rotating or the motor is rotating, the motor is rotating around a shaft. So this is our shaft. So this motor is rotating around the shaft. So torque is, so you have to, in this case, you have to measure the torque to what is the torque is generating for due to the rotation of this motor. So once again, I am repeating, torque is a measure of force that can cause an object to rotate about an axis. So what you are actually measuring? You are measuring the force. So so therefore this can be measured by using simple strain gauge configuration. So here I have an example of a stock sensor by using simple strain gauge operation, that is bridge that is known as bridge configuration. Here we have 4 strain gauges. You can see 1, 2, 3 and 4, and we have placed these strain gauges in this way. So these 1 and 2 strain gauges are on top of this shaft or whatever. So this is rotating. This is rotating, fine. So this is rotating. This is a kind of shaft which is rotating, fine. Now you have placed 2 strain gauges. I think I have already told you what is strain gauges. So you have to place 1 strain gauges on top of this shaft, and these 3 and 4 at the back side of this. This back side of this particular rod or shaft. Fine. Now how to measure the torque if this shaft is rotating? So let's see. So as I told you, the shaft is rotating. So once again, this strain gauges, if you see this carefully, the strain gauges are placed in 45° to the axis of the rotating. So see, all the strain gauges are placed at the 45-degree angles, right? And two of them are on the top side and this side, and another two of the at the back side of this shaft. Okay, so you have a stationary rotating part, and this bridge configuration we have on the shaft, and you have another stationary part. So that is the stationary part for the signal conditioning. Coming directly to the measurement working principle. So here, when the torque is there, for example, if the torque is in this direction, so what happened? So you have two sensors are there. So these two sensors on this sense, this 1 and 1, 2, 3, 4. If I write in this way, 1, 2, 3, and 4. So if you see that this 1 and 2 sensor, these two sensor will be at elongation, and 3 and 4 are at the suppression. Okay, so that means there is a tensile force and there is a uh, there is a suppressing force. So that means there is a, if you know, I already know that if you elongate your strain gauge, that is, you know, R equal to rho L by A. So if the L is changing, so R will also change. Okay. So therefore, by the bridge arrangement, what you will find is that in case of bridge arrangement, bridge arrangement, in if we come once again in this bridge arrangement, so there it will find that in bridge arrangement, so so in this 1, 2, 3, 4, so that means if your bridge is balanced, now due to the torque, the elongation and the suppression works, happens to this strain gauges. So therefore the balance of the bridge will be disturbed, and due to by measuring the balance, by measuring the output voltage of this particular bridge, you can measure the torque. Okay, that is the basic principle of the torque measurement by using the strain gauge. Although there are several another methods, by measuring the force also you can measure the torque. By measuring the speed you can measure the torque, but it is the simplest kind of measurement principle of the torque, for measuring the torque. Fine. Now coming to the, so there are also another sensors are there. I will show you some interesting video on that. But before that, so there is another indication technique, identification technique, that is, mostly used, or nowadays, all of the most of the industries as well as the inventories are used the techniques to identify the thing. This is also kind of detection technique. So you can, this is not a sensor, but as it is a identification technique, so we have to learn this for the for this particular course. So this is the RFID. There is full form is radio frequency identification tags. Now how a RFID works? What is the principle behind it? In a RFID system, you will find one RFID reader and there is a one RFID tag. So in general, the tag is connected or it is attached with the object. So RFID reader will actually continuously sending the waves, that is the radio waves particularly. So that radio waves will be, if there is a RFID tag, so due to the electromagnetic coupling or the inductive coupling, I will tell you what is this. So due to that, so you will find there is some reflection from the RFID tag, and by measuring the reflection from this RFID tag, so RFID reader will tell you that there is an object or not. Fine. So that is the main basic principle of the RFID based identification system, right? Now coming to the more details about the RFID system. So as I told you, there is a RFID reader and RFID tag, and RFID tag can be of three types: active tag, passive tag, and semi-passive tag. So what are these things? So in active tags, you will find the tag itself has a power supply. That means whatever the signal you are receiving, that signal, the I mean for the, so reader will send a radio waves and tag will receive that. So if I tell you the passive first, that will be clear for you to understand that. In what will happen in case of passive tag is that in passive tag there will be no uh, power supply. So whatever the radio waves will come into the RFID tag, that radio waves will act as a energy source for the passive RFID tag, and that will actually energize the tag, and due to that energization, so there will be reflecting wave will be created, and that reflected wave will be read by the RFID reader and to detect a object. On the other hand, in case of active tag, there is a external power supply which will actually give you the reflecting wave. So you can easily understand that this passive tag is generally used for lower range of detection, where the range of the detection of the object is very low. But in case of active tag, as it is generating the reflecting wave by using a power supply, so the strength of the reflecting wave to the reader will be very high than that of the passive tag. So therefore the active tag is generally used for the long range. Fine. Now come, you may ask me why I use the RFID tag where there is a barcode. Okay, so that the answer is something like that. In barcode, the barcode is generally used for line of sight detection. So that is a limitation of the barcode system. You may have seen that in Big Bazaar there is a barcode is always there in any item. So there is a scanning laser scanner is there, and that they are clicking on that barcode, and if that barcode is not line of sight, very often you will see this the object is not detected. Wherever you, if you go to the any Reliance Trends or any kind of other I mean the it is kind of the clothes like a kind of thing like Reliance Trends or any other big the larger kind of shopping mall. What they have is that they have it RFID tag. So for example, if you have gone if you have visited some electronic store, they are using the RFID tag with their electronics item. So if some thieves are there who are trying to who trying to get that item and keep that item in their pocket. So there you have seen that there is a two vertical arrangement is there at the gate, so that will automatically detect, and that is not maybe that shouldn't be in the line of sight. So what I want to say is that the barcode is kind of line of sight measurement, but wherever the RFID is concerned, the RFID is not is the line of sight measurement. It may be not maybe in line of sight means not directly at the receiver and the uh, sorry, the transmitter and the receiver not are in the same line, but for the RFID system, but in case of barcode, that they are should be at the same line. Okay, so this is the main important part. This is the main advantage of the RFID system over the barcode. Not only this, in barcode, if the barcode is tempered, so you can't detect the barcode. But in case of RFID system, as this RFID is generally is a kind of antenna based system, so these are actually it's very difficult to tamper because they are close. They are actually situated in a closed system. I will show you how it looks like. Now in a RFID reader, this is a typical diagram of a RFID reader. Here you can see there is a microcontroller you have, and there is a RF signal generator, and this RF signal generator will first send some radio waves, and if that radio will be received by the tag, and the tag will send some, and after the receiving of the radio waves, the tag will once again send some another radio wave that will be received by the receiver at the RFID reader part, right? Now this is the I mean this is the particular example, or the particularly diagram of a RFID. You can see they are closed system. So this is the antenna. So this antenna is actually encapsulated in between these two part. Okay, and this is very low cost system because this is a simple metal patterning, nothing else. Now coming to the RFID tag, there is also controller, rectifier circuit, transponder and memory. So but you have to keep in mind that for a passive tag, all these things are there, but all these controllers, memory, rectifier circuit are energized by the radio waves which was sent by the what reader. Okay. Now, coming to the frequency of operation of the RFID tag, there are low frequency region which is up to the 10 centimeter, high frequency region up to 1 meter, and ultra high frequency region that is in range of 10 to 15 meter. So you can easily understand that if you increase the frequency of the radio waves, that means you are increasing the power of the radio waves. So therefore you are increasing the range of the measurement, range of the identification. Now there are two different working principles for the low and high frequency range and the ultra high frequency range. For in case of low and high frequency RFID tags, they are actually use the inductive coupling method, that is also for the near field coupling, and ultra high frequency range use the electromagnetic coupling method. Okay, in inductive coupling method, which is used for low frequency range, are consist of three things. That is that will be possible that the reader is actually doing three things. First is induce enough power into the tag. It will send radio wave, that is the induce, that is the enough power to for the working of the tag, and then it will synchronize the clock to the tag. That means whatever the radio waves it is sending, that has the frequency. So due to that radio waves, the tag will energize, and that will create some voltage, and that voltage is also synchronized with the frequency which is sending by the reader, and the sending radio waves also act as a carrier for return data from the tag. Now this is the detailed diagram of the inductive coupling. Here you can see the once again the RFID tag is sending the radio waves, and this is the passive receiver. If I this is the passive tag, and this is the RFID reader, and this is the RFID passive tag. It has rectifier, controller, clock and load. So load is what? Load means there is a connection or not, or there is a object or not. So that means when there is an object, that may be open, or when there is no object, that may be closed. Simple things. So see how this works. So first the RFID reader will send a radio wave, and that radio wave is sufficient to energize the controller of, there is an antenna, that antenna will receive the these radio waves and energize the controller. That means these waves are in these radio waves, on the other hand, works as a power supply for this controller. And what this controller does, as I told you, the radio waves has a frequency. So this frequency actually the generated voltage is also in same phase with this frequency, and that's how the clock will be synchronized. And now, as the voltage is generated, and if you apply a voltage to this load, that means, as I told you, the load means there is an object or not. So that means if the load is there, for example, if the circuit is closed, so that means there will be current. If there is no load, so if the switch is open, so that means there will be no current. So that means, is the simply is thing is that when there is a object, that when there is a object, so switch is closed, you will get the current, and that current will generate a waves, and that waves will detected by this reader. Fine. And when there is no object, so this load or this circuit is open, so they will not get any current from this output, so there will be no no signal that is generated at this particular tag. So the reader will not detect any signal. So, and you can understand it in vice versa. Okay. Now in far field coupling, what is happening? In far field coupling, as I told you, this is a kind of magnetic electromagnetic coupling. So these are actually generally depends on the active type of tags, and generally use the backscattering signal to detect. So these are the signal. Once again, the RFID reader will send a signal to this load, and this load, the presence of load or the presence of object can be detected by a backscattered signal, which is generated by this active tag. So if there is a object, so backscattered signal will be generated. So this is known as the backscatter signal. This is totally different from the inductive coupling method. Okay, that's all about our today's class. Now I will show you some simple video on some different sensors, like gas sensors, viscosity sensors, LiDAR technology, and some basic idea about the encoder. So let's start with the encoder. And one by one, I will show you how how the gas sensor works, how a viscometer works, how a optical pressure sensor works, and what is the LiDAR technology.
An encoder is a device that is used in many industries to provide feedback. In the most basic terms, an encoder, regardless of the type, which we will cover later, senses position, direction, speed, or counts. And the you never misuse motion, you never miss signal. That signal is then sent back to a controlling device, such as a PLC, and is interpreted, meaning scaled, to represent a value that will then be used within the program. Some of the technologies involved in encoders are magnetic, mechanical, resistive, and optical. Optical is the most widely used encoder motion translating technology. There are different types of encoders, such as absolute and incremental. We will describe those in greater detail in a future lesson. But for now, an example of an incremental optical type encoder uses a beam of light that passes through a disc that has opaque lines in a specific pattern, somewhat like the spokes of a wheel. On the other side of the disc is a photosensing device that will interpret the light based on the pattern on the disc. Picture a shutter blocking and unblocking the light. The pulses of light are then converted to an electrical signal to be sent back to the processor through the encoder's output. Encoders have a wide range of uses, which include closed-loop applications such as servo or VFD control, measuring, and counts. Here are some examples of processes that may use an encoder. For VFD control, you may be running a pump on a VFD to fill a tank full of a liquid. You are requesting a certain speed and want to verify that the pump's VFD is at the requested speed. An encoder on the VFD may be used for feedback of speed. Next, let's give an example for a measuring process. In this application, you will need to cut some aluminum product to a particular size. You are passing a long roll, meaning hundreds of feet, of the aluminum sheet through a cutting mechanism. You need to determine the amount of aluminum fed so that you can cut the sheets to the proper size that will be used in a separate manufacturing process. An encoder, attached to the conveyor and reading the material that is feeding through your cutting assembly, will indicate the length of material that has been fed since the last cut. That feedback can then be used to adjust the cutting blade to sever the length required. For an example of counts, consider this process. You have a conveyor line that has bottles running on a conveyor. They are counted by a photo eye sensor when entering the assembly. They have a cap with an aluminum tamper-proof foil on top that needs to adhere to the bottle. Once the foil is sealed, the bottle will then move down the conveyor line and verified that it exited the cap sealing assembly via an exit photo eye sensor. Some of the requirements for this station are: the same number of bottles that enter the assembly must exit in a predetermined time frame. The bottle must not remain in front of an entrance or exit sensor. The bottle must not be exposed to the inductive sealer longer than a predetermined amount of time. You must make this assembly flexible enough to handle many types of bottles and entrance and exit sensor placement. Consider a prescription bottle. Easy, right? No handles, just a bottle that is a standard size. Now, consider an antifreeze bottle with a somewhat small cap and a very large handle. How in the world are you going to meet the requirements for the machine and remain flexible? If you put a pill bottle in, yep, easy peasy, right? Bottle in, seal, bottle out, no sensors blocked. If any of the requirements fail, bottle in, seal, tips over and isn't counted out, machine halts and alerts on operator of a malfunction. How about the antifreeze bottle? Bottle in, cap passes in front of an entrance sensor, bottle counted, then the handle. The system faults because it sees a blockage at the entrance. How do you tell the machine that this is expected behavior? An encoder, of course, and a selector switch for a setup mode. To set up, insert your product, in this case the antifreeze bottle. You make sure to feed cap first, and it must contain a foil. Your program reads an entrance on the sensor and records an encoder reading, as well as determines that this is a cap and records that fact. Your program then reads another entrance and determines that this is not cap. It must be some other acceptable part of the bottle, possibly a handle. The single bottle continues down the line, where the exit sensor is triggered. At that point, you again record the encoder value. You now have an encoder count that registered at the entrance and exit. In the code, you subtract the entrance from the exit, and you have a bottle count. You now know precisely how long it will take that bottle to move through the system, meeting the must enter and exit in a predetermined time frame, in this case, encoder counts. You have also made the flexibility aspect of different types of bottles, as well as being able to place the entrance and exit sensors any reasonable distance apart. When back in run mode, the code knows that there's a handle to ignore when it comes into the process, and doesn't fault the machine. You register the encoder at each bottle entrance and predetermine when the bottle must exit. If the bottle doesn't exit the machine in a timely manner, which is based on your projection and the current encoder count, the machine faults. This is a great use of an encoder that is fully configurable. Count in, count out, subtract, done. Don't miss the next lesson, where we are going to discuss incremental and absolute encoders. Want to learn PLC programming in an easy-to-understand format? And take your career to the next level?
At Cambridge Viscosity, our patented sensor technology sets us apart from other viscometer manufacturers, making us the worldwide leader in small sample viscosity. Our online viscometers install directly into the process either in-line or in-tank, providing the most up-to-date readings. With only one moving part, a piston is driven electromagnetically through the fluid inside the measurement chamber at a constant force. A deflector positioned over the piston moves fluid into the measurement chamber, while two coils move the piston back and forth. Proprietary circuitry analyzes the piston two-way travel time to measure absolute viscosity. An internal temperature detector senses actual temperature inside the measurement chamber. The system can calculate temperature-compensated viscosity, which increases its accuracy under the ever-changing environmental conditions for direct comparison with laboratory data. The electronics can also provide the current shear rate at the measured viscosity. Since all the parts that can become wet are made of stainless steel and the piston is in constant motion, the sampling area is continually scrubbed clean to prevent fouling. The system holds its calibration and requires little to no maintenance. It is insensitive to flow, vibration, particles, or entrained gas. Data from the sensor is processed in the electronics in accordance with ASTM D7483, providing correlation to ASTM D445. Measured data is displayed directly on the analyzer. Output outputs are available in 4 to 20 milliamps and Modbus to allow customers access to information where they need it most. The user interface can be either hardwired or accessed on a smartphone via the wireless option. The UI allows for changes in settings, units, and calibrations, as well as downloading of the error log and data log. For more information about our viscosity measurement solutions, visit www.cambridge.
Now I would like to show you the optical pressure sensor.
Hey guys, welcome to Skill Link. In one of our previous videos, we talked about how optic fiber air in it. At a fixed position, let's keep a laser beam. Optic fibers are used for communication. Today, we'll discuss how they can be used to measure pressure. Let's take a balloon and fill air in it. At a fixed position, let's keep a laser beam. Let's switch on the laser beam such that it hits the half-filled balloon and is reflected back. Now, let's fill the balloon completely with air and strike a light on it again. Now, we will notice that the ray travels a shorter distance and gets reflected back. A similar idea is used in fiber optic pressure sensors. In this video, we'll be discussing the construction, working, advantages, disadvantages, and applications of the fiber optic pressure sensor. The construction of the fiber optic sensor is very simple. The sensor consists of an optic fiber and has two reflecting surfaces. The first reflecting surface is semi-reflective and is coated with a dielectric medium. The second reflecting surface forms the diaphragm, which is placed in front of the optic fiber. Behind the second reflecting surface, the unknown pressure to be measured is placed. The two reflecting surfaces are kept at a distance of Ls. And this cavity between the two surfaces is termed as Fabry-Perot cavity. By measuring the distance Ls, the unknown pressure can be determined. Now, white light is passed to measure the pressure. Now, the question may arise, why specifically white light? We know that white light is a combination of several other colors having different wavelengths. When the light is passed through the fiber, a part of the light hits the first reflecting surface and bounces back, and the rest reflects back from the second reflecting surface. After reflection, these lights get superimposed, and by measuring the distance traveled by the light, the pressure can be determined. By calculating Ls, this unknown pressure will be determined. The time difference between the two rays can be given by T equals 2Ls by C, where C is the speed of light in vacuum. Now that we've seen the construction and working, let's discuss the advantages of the fiber optic pressure sensor. One of the main advantages of using the fiber optic pressure sensor is that they are immune to electromagnetic waves, and because of this, the reflected signal gives accurate measurements. The size of the optic fiber is also very small, and this makes it possible for them to be in narrow areas where other sensors find difficulty in being placed. Finally, the fiber optic sensor has a fast response time. Next, we have the disadvantages of the fiber optic pressure sensor. The fact that they are highly sensitive can sometimes make them susceptible to acoustic waves. Furthermore, their thin size makes them less robust when compared to other sensors. Now let's check out the applications. Since they are immune to electromagnetic waves, they are very useful in harsh environments. They are extensively used for medical purposes, for measuring pressure in the lungs, digestive tract, brain, etc. With this, we will end our video here on fiber optic pressure sensors. We'll see you in the next.
Now it will be the gas sensor. Now it will be LiDAR technology.
Hey friends, welcome to the YouTube channel all about electronics. So in this video, now as its name suggests, this technology uses the light waves or the light source to measure the distance between the objects. Or in another way, we can say that it is used in the range finding applications. So now this is not a new technology, and in fact it is being used since last more than 50 years. And in 1960s, it was first used to measure the distance between the moon and the earth using the lasers. And nowadays, it is being used in so many applications. And maybe in the future, you will see that your self-driving car will be equipped with this lidar system. Now, if you see this term lidar, it sounds very familiar with the term that is known as the radar, and many of you might be already knowing about this radar system. So now in terms of the working principle, this lidar and radar both are quite similar. So let us find out in this video what is lidar, how it works, and what are the different applications of this lidar system and how it is different from the radar system. So first of all, let us understand how this lidar system works. So now if you see any lidar system, the laser and the detector are the two of the main components which you see inside this lidar system. And most of the lidar systems works on the principle of time of flight. So in this principle, the laser in the pulse form is targeted on the object, and the reflection or the scattering from the object is measured by the detector. And at the detector side, the timing between the transmitted pulse and the received pulse is measured. So let us say the distance between the lidar system and the object is capital D. So now if we know the timing difference between the arrival and the transmitted pulse, then using this simple mathematics, we can calculate the distance between the lidar system and the object. And here, this velocity of this transmitted light pulse will be at the rate of speed of light. So this is the basic principle how every lidar system works. So now if you see the working principle of radar system, even radar system works on the same principle, that is time of flight principle. So now let us exactly understand what is the difference between this lidar system and the radar system. So now if you see the term radar, it stands for the radio detection and the ranging. So instead of light waves, in case of the radar system, the radio waves are used for the measurement. So now if you see the electromagnetic spectrum, then you will notice that the radio waves which are used in the radar system are millimeter waves, while the light waves which are used in the lidar system are almost 3 order less in dimension than the radio waves. So these radio waves cannot detect the objects which are very small in the dimension. While using the light waves, we can even detect the very small objects. So using this lidar system, we can achieve the much more precision. So because of its precision, these lidar systems are used for the 3D mapping of the object or even for the surface scanning of the object. And using this lidar system, we can even scan the buildings as well as the different terrains. While the radar systems are used in applications where the exact size and shape of the object is not important, but the detection distance is more important. So basically they are used in military applications or in air traffic control, where the detection of the object is more important rather than the size and shape of the object, or even they are used in some range finding applications. Now the advantage of radar over lidar is that it works even in the harsh environment. So it even works in case of the rain, fog or even snow, while the lidar system cannot work in such harsh environment. So now whenever we are discussing the different technologies which are used for the range finding, so let us also mention the one more technology which is used for the range finding, which is known as the sonar. So in this sonar technology, instead of the radio waves or the light waves, the acoustic waves are used for the range finding or measuring the distance. And mainly this technology is used for the underwater applications. Alright, so here is the quick comparison between the lidar and the radar system. So as I said earlier,
maybe we'll late by some 5.
Now I would like to show some case studies on sensor different industries like steel industry, battery industries.
Excuse me, sir.
Yes, please.
Uh, Sir, sorry to disturb, but we have a class
Yes.
of cyber physical system from 11, sir.
Okay, okay, no problem. So I will send it by the WhatsApp.
Okay. Thank you, sir.
Okay. So thank you very much. This was probably the last class for this course from myself. Thank you for your attention throughout the classes. Thank you very much and best of luck.
Thank you so much, sir.